A warm welcome to all of you people, those who are watching this video. This is the first tutorial I am going to share from the community called the Era of Chaos. Today I am going to discuss about Euler's number and Euler's numbers related some facts and consequences. So without delaying, let me start the session. So you know that the number e, so you have already seen something called this e. This e is also known as Euler's number. So don't confuse with Euler's constant. Okay, so that is something different, and in another session I will definitely discuss with Euler's constant. So that is different. So Euler's number. So what is Euler's number? So Euler's numbers is a mathematical constant, you can say, which is approximately equal to, so Euler's numbers, so E, the Euler's number is approximately written as 2.718, okay, 28 and so on. Okay, so that can be characterized in many ways. Okay, so it is the base of natural logarithms. So it is the limit of so for this sequence called 1 plus 1 plus 1 by n, say suppose this is the sequence n, and if I just take a limit of an as n approaches to infinity, so as n approaches to infinity, it's an expression that arises in the study of compound interest, and it can also be calculated as the sum of the infinite series, right? So E, so if I just do a very known expansion of E, so E, this E equals to, in the summation format you can write it as n running to 0 to infinity 1 by factorial, and it can be expanded in the form of 1 by 1 by 1 factorial. So 1 factorial, you know how to break it, and plus 1 times 2 factorial, that is written as 1 times 2 plus 3 factorial, that can be written 1 times 2 times 3 plus dot 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 and so on. So this is how we represent E. So I am interested to show you that why this E, or how to prove E is a irrational number. Okay, so before going to prove that E is a irrational number, so as you know that I am quite interested about some probability and stuff, so let me show you one interesting thing of probability, that is the Bernoulli trials, and how this E, the Euler's numbers, is quite associated while developing this Bernoulli trials. Okay, so let me show you a graph. Just wait a while. Sorry, so let me insert files. So if I just take this graph, yeah, so let me adjust it. So you see this graph here, okay? So so you see that the number E itself also has an application in probability theory, okay? So in a way that it is not obviously related to exponential growth. Suppose that again, so let assume a scenario. Say suppose that a gambler plays a slot machine that plays out with a probability of 1 in n and plays it n times. Okay, so let me write this problem. So suppose yeah, suppose, yeah, don't judge me by my handwriting, so it is not quite good, so try to understand. So suppose that a gambler plays a slot machine that plays out with a probability of 1 in n with and plays it n times. Okay, so plays out with a probability probability 1 of 1 in n and plays it n times. Right? So as n increases, the probability that gambler will lose all n bets approaches towards 1 by e. Okay, so let me write that as n increases, the probability that gambler will lose all n bets approaches one by e. Right? So for n, if I take n equals to 20, for n equals to 20, okay, so this is already approximately already approximately what it would be. So that will be approximately 1 by 2.789509 and so on. Okay, so this is an example of a Bernoulli trial process. So you see the graph. Okay, so the graphs of this probability p of not observing the independent events, each of the probability 1 by n after n Bernoulli trials, right? So and one by p versus n, it can be observed that as n increases. Okay, so each time the gambler plays the slots, okay, there is a 1 in n chance of winning. So playing n times is modeled by the binomial distribution, which is closely related to the binomial theorem and the Pascal triangle, you know. So the probability of winning k times out of n trials. So if I just write it mathematically, okay, so what the graph is saying, again let me write this. So what is the graph saying? So graph of this probability p of not observing. So p of not observing, independent events, independent events, each of probability 1 by n after in Bernoulli trials. In Bernoulli trials, right? So as I was saying, that each time the gambler plays the slots, there is a 1 in n chance of winning. So playing n times is modeled by the binomial distribution. So what I was saying, that the probability of winning, the probability of winning k times, okay, k times out of n trials. That is probability, if I write it as probability k wins of n, which is modeled as n choose k, okay, that is 1 by n to the power k. So 1 minus 1 by n. Maybe some sort of those who are probability enthusiasts and those who are quite aware about how to deal with these probability problems, you maybe know, or you are aware with these Bernoulli trials and these sort of problems. So in particular, the probability of winning 0 times. Okay, so if it is if k equals to 0, okay, if k equals to 0, that is the probability of 0 wins of n, okay, so that will be what? That will be 1 minus 1 by n to the power n, okay. So you see, again I am returning to this graph. So it can be observed, or that Bernoulli trials, what I am saying. So yeah, let me add one more thing, that Bernoulli trials, okay, and 1 by p and 1 minus p versus n. Okay, so it can be observed that as n increases, the probability of 1 by n chance event never appearing after n tries rapidly, which is converges to 1 by e. So the limit, okay, so the limit of this expression, okay, so this, so if I just take the limit of this, so again this limit of this, what it would be. So if I just tend towards to infinity, so if I just take the limit, so the limit, so limit of n tends to infinity of 1 minus 1 by n, so this is n, so what it would be? So it would be 1 by e. So you can calculate that this is 1 by e. So again I am repeating, it can be observed. So in using this Bernoulli trials, in the 1 by p versus n, it can be observed that as n increases, the probability of 1 by n chance event never appearing after n tries rapidly, which is converges to 1 by e. Okay, so one important and very important while solving problems, it will occur that the inequalities. So what we deal in inequalities with, so the number that is e is the unique real number such that, so let me write this, so inequality, okay, so inequality so the number, as I am saying, that the number e is the unique real number such that it is bounded, so e is bounded, this is 1 plus 1 by x, okay, raised to the power x plus 1, and 1 by 1 plus x, 1 by 1 plus 1 by x, 1 over x raised to the power x. So for all x belongs to this positive integer. So also we have the inequality which is follows as e to the power x, which is greater than or equal to x plus 1. These are some consequences, so I am leaving to you that you can prove yourself and send it to me, to my mail ID. So I'll send you, and in the description box I will paste the mail ID. So for all real x with equality if and only if x is 0, and this e is the unique base of the exponential for which the inequality, that is the a to the power x is greater than or equal to x plus 1. So you can prove yourself, and that holds for all x which is to real. So I can show you one thing using graph. Yeah, wait for a while. So yeah, so you see this graph, okay? So what you can see, so this is the exponential function y equals to 2 to the power x and y equals to 4 to the power x, okay? So if you just plot somewhere the y equals to 2 to the power x and y equals to 4 to the power x, which intersects, okay, the graph of y equals to x plus 1, okay? So I am writing that. So yeah, so let me choose another color. So you see this blue line and this red line, okay, which is y equals to 2 to the power x, and the red one is y equals to 4 to the power x. So you once you can verify this, if I am wrong somewhere, so you can counter me. Yeah, so it intersects, okay, so it intersects, yeah, so it intersects y equals to x plus 1, right, and respectively at x equals to 1 and x equals to minus half, the number is the unique base, okay? So at you can cross check, okay? I always support that you should cross check. Maybe I could be wrong somewhere. So if x equals to 1, okay, x equals to 1 and x equals to minus half, okay, so the number E is the unique base such that e to the power x, sorry, such that y equals to e to the power x intersects only at x equals to 0, right? So we may infer that E lies between 2 and 4, right? So E lies between 2 and 4. This is important. Okay. So so let me come to the point where I am really excited to show you that E is irrational. So we can prove there are different way to show you that E is irrational. One is quite difficult to understand and one is quite easy to grasp. But I will show you first the which is quite easy to grasp. But before going to prove that E is irrational in the easiest way, you have to aware with some consequences, some mathematical facts. Okay, so we'll prove the irrationality of E using squeeze theorem. Okay, so what is squeeze theorem? Okay, or sometimes you may heard about the what is say the sandwich theorem. So both are same thing. Okay, there is nothing different in the concept. So one definition is for so the idea is same. We can use this for sequential definition for it is applicable for sequential definitions as well as the function. Okay, so what is the theorem says? So first, if, so let me write, so let me use another page. So let me choose black. Yeah, so the squeeze theorem for sequences. So I am not going to prove squeeze theorem right now because this is not our concern here. So I will just state the squeeze theorem and I will provide intuitive definitions or understanding or visuals which can help you to understand what do you mean by squeeze theorem and how I will apply this squeeze theorem in our problem solving. Okay, so if I write how to justify, yeah, so squeeze theorem. So okay, so squeeze theorem. So what does squeeze theorem says? Yeah, so if an and bn and cn be the sequences of real number R, so then for an lesser than equals to cn and cn lesser than or equals to bn for all n belongs to n, where this for some n, okay, for all n belongs to n, for some n, okay, for some n. So this is not yeah, So n belongs to natural number definitely. Okay, so where you can state that okay, so where uh, for some n uh, for some n where n belongs to set of natural numbers. Okay, therefore if we take the limit, so let me write it in another color. Then the limit, we take the limit of n, okay, and the limit of bn. So the n approaches towards infinity, and here the n approaches towards infinity, which is equal, that is the same limit. Okay, then Cn okay, the limit of Cn, okay, the limit of Cn, that is n towards infinity, is n. It means what? It means that when a sequence lies between two other converging sequences with the same limit, it also converges to this limit. Okay, so the main idea or the main motive of squeeze theorems is that the limit of a function or sequence that is trapped between two other functions or sequences. So the squeeze theorems is used in calculus or in the analysis of this mathematical analysis, typically to confirm the limit of a function or limit of a sequence via comparison with two other functions or sequences whose limits are known. So it was first used geometrically by the mathematician Archimedes, and there is one more mathematician, I just forgot that name. So in an effort to compute pi. Okay, so as I was saying that when a sequence is when a sequences lies between two other converging sequences, so let me write it. So this is the formal mathematical definitions of squeeze theorem. Okay, let me highlight it. Yeah, so this is the highlighting portion. So if you want to take notes, take it carefully. So this is the definition, this is the mathematical arguments I have stated here, and that's how it is denoted. Okay, so intuitively or for a visual perspective, what we can claim that, say let me use some different colors. Okay, say this is my Cn. Okay, so here it is this, sorry, so here it is my Cn, here it is Cn. Okay, so Cn is okay, so yeah, this is Cn. Okay, so you can take this dot 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 dot, and it is converging towards a point. Okay, again here it is Bn. Okay, okay, let me write it as what I can write. This is Bn. Okay, so let me write it as Bn. Yeah, so this is Bn. Yeah, Bn, and let me write another sequence. Yeah. So this is say n. Okay, this is also going this way. Okay, towards a point, and here it is my Cn, right? Here it is my Cn, and Cn also somehow approaching towards a point. Sorry. And that's how it is approaching. Cn also approaching. Okay, and this, so this is the point. So okay, so this is the point. Say this is the what it could be. So this is the point. Say it is A. So when a sequence, what are you are saying, and I am repeating it. So when a sequence lies between two other converging sequences with the same limit, it also converges to its limit. So this is the visual definition or visual meaning of the squeeze theorem. Say so this is the meaning, or this is the way we can define the squeeze theorem. Okay, so same for the functional cases also. So if I just write that say, so let I, so if I be an interval, okay, I be an interval containing the point A, containing the point A, and let G and F, and you take H, which is the function, and it will define on I. Okay, so G and G, F, and H. Okay, so this be function, be functions. Okay, functions defined on I, right? And except possibly at A itself. Suppose that for every x, okay, for every x in I not equal to A, so that's how we have gx, okay, which is lesser than or equal to f of x, okay, and that is lesser than equals to h of x. So, and that's how, if we put limit of x tending towards to a, that is gx, which is limit of h of x, and this x approaches towards a, it will be L, and then limit of x to approaches to a, f of x is L. Okay, so that is the main understanding or main concept or the mathematical we can represent from both sequentially and functionally of the squeeze theorem. So if you see a problem, I can discuss that problem. I should discuss, because otherwise you won't understand, those who are not aware about squeeze theorem. Okay, maybe in another if I take real analysis session, definitely I will make a playlist about real analysis. So there I will definitely discuss about squeeze theorems in very detail, as well as I do some problem solving sessions on squeeze theorem. So let me discuss a problem which will help you to understand what is squeeze theorem and how to implement these things. So, and I will use a graph. Okay, so let me change the page. So the limit. Okay, so limit x approaches to 0. Okay, and the function is x square sine 1 by x. Okay, so this so if I take so how to solve. So this limit cannot be determined through the limit law. Okay, we cannot because if you take limit, okay, so if you take limit, why we cannot determine through the limit laws? Because if you take limit of x approaches to 0 and sine 1 over x, okay, so that doesn't exist. So however, by the definition of sine functions, okay, so what is the definition of, so if I just apply the sine function definition, okay, 1 by x, so this is it, right? So it follows that what? So it follows that minus x square and this positive x square lies between x square sine 1 over x. Okay, so since limit x tends to 0, okay, so limit x tends to 0 minus x square, okay, which is limit of x tends to 0, x square equals to 0. So if we apply the squeeze theorem in it. Okay, that means what? So it means that limit of x approaches to 0, the x square sine 1 over x, that must also that also be 0. So these things also be 0. So it means what? It means, so graphically, if I draw this, so this is your xy coordinate. Okay, so if I take red color, okay, red, so okay, okay, and not like this. Let me draw this properly. Sorry. Okay, don't judge me by this drawing. Okay, and if I take another color, blue, so this is also this. Okay, and if you just do this sort of things, okay, and this is, so it will look like this. I am not able to draw it properly. Okay, so again I am trying to draw it for your understanding purpose, and it is quite difficult for me to draw here using this. So yes, so you see, so if you just draw this x square sine of 1 by x, and so you see that somewhere, so it will be more densed here. Okay, so I am not able to draw this more dense here, so it will more squeezed here. Okay, so you so for your understanding purpose, what I want to claim is that x square sine of 1 by x. So I guess this much of drawing is enough, quite enough to make you understand that what I want to say is that this x square and sine of 1 by x, okay, being squeezed, okay, squeezed in the limit as x goes to 0. So you can see that how this function being squeezed. So this is the squeezing point. This is the point where the things is going to squeezing. Okay, so yeah, so this is the point. This is the area. More, if I just take more denser, so you will see so how things are getting squeezed here. Okay, So yeah, so let me go back to our problem. So how to prove that E is irrational? Okay, so we can prove the irrationality of E using squeeze theorem. So we can use three tools or the three properties of limits to prove that E is irrational. So what are the three properties I will use? So the three properties we are going to use is that one is a limit n approaches to infinity, and this summation m running to n plus 1 up to infinity, and the n factorial by m factorial equals to 1, sorry, this is equal to 0. Second is same thing, okay, so limit n approaches to infinity, okay, summation n plus 1 up to n factorial by, so if I just multiply 1 n here, so it will turns into 1. Okay, and one more fact which is very important, that is if limit n approaches to infinity, an is equal to a, and limit x approaches to a, the function is equal to L, then the limit n approaches to infinity f of an is equal to L, right? So how do we use the first property? So using first property, so we'll evaluate, okay, the first property here, okay. So let me start from the first property. Yeah, so the first property, sorry. Yeah. So if I just, so I'll first evaluate this summation part, okay. So the summation, which is running to n plus 1 up to infinity, so under this summation n factorial by m factorial, again this summation n plus 1 up to infinity. Now how I will break it? So I will break it down this m factorial as m times m minus, this is m minus 1, and that is up to, that it will goes up to n plus 2, okay, n plus 1 and n factorial, right? So in the next step it will comes like this, m equals to n plus 1. So it is something, so m factorial is collapsed with these terms, okay. So I'm starting from m times m minus 1 and dot 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 so on, and then I am starting, okay, so it will so it will goes up to the term 3 times 2 times 1 and so on, and then I am adjusting this n factorial here, okay. So here by doing this step we will understand what I want to do with here. So n plus 1, okay, n plus 1, n plus 2, and dot 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 so on, this m, okay. So I'm just eliminating here this n factorial, because this n factorial terms is eliminating in this step. And here why I am writing in this format, because I want to do that is take m that finishes off this product and rewrite it as some something like this, this format, right, in this format it will written like n plus m minus n in this format. So I want to rewrite this entire m factorial and things in this format. So I am writing this, okay. So I do that because I want to, why I want every term in this product here to be n plus something, okay. So here, so let me write it. So what I want, that is again, so this term, so 1, so n plus 1, n plus 2, dot dot dot, n plus m minus n, this, okay. So this is n plus something terms. So this is, so as I was saying that I want to do that is so I want to take m that finishes up this product, this entire product, and rewrite it in this format, okay. And I do that because I want every term in this product here to be n plus something. Something means some other terms, okay. So if you notice these entire things, so notice that if I multiply out entire denominator, I have polynomial in n, even we have exactly m minus n terms, right. So here it means that, so here it is n to the power m minus n term, m minus n plus more. So this more means that that is the positive terms, just like how it multiplies out. Okay, right? So as I was saying that this is nothing but n to the power m minus n plus more terms, and these more terms is a positive terms, just like how it multiplies out. Okay, and this I am denoting this m minus n equals to k, where k is running 1 to up to infinity. Okay, so therefore I can write it these things. So this is a very non-formal way to write. So therefore summation m running n plus 1 to infinity, okay, and this entire things, okay, n plus 1, n plus 2, that is up to n plus m minus n. Okay, so you can write in this format as well. So this is one, and next step we'll write this m equals to n plus 1 up to infinity and 1. So yeah, so n to the power m minus n plus, you can write it more terms. Okay, so this m minus n is denoted as k, and this more terms, okay, that is lesser than this. So it means what? It means this is the larger part. This is larger. So as this increases, okay, then whole term, this whole 1 by 1 over n to the power m minus n, and this more terms, this entire expression or things will decreases. Okay, if this increases, then this entire things will be decreases. That is that is why it is lesser than, and this is the things. So if we evaluate, okay, so let me clear this out. Okay, so if we just evaluate this, then this will be 1 by n by 1 minus 1 by n, and it will be 1 by 1 minus by n. Oh, no, sorry. N minus 1, sorry. N minus 1, yes. So we can conclude that, what we can conclude? We can conclude that this in factorial by m factorial, these terms with summation m equals to n plus 1 to infinity, this is lesser than 1 by n minus 1. As you know, this is definitely a positive term. This term is positive, so this is a positive term. Okay, so that is why it is, we can write it 0 here. So n minus 1, sorry, so n minus 1 and this is positive, so 0. So now we have setup of squeeze theorem, right? So now let me write it properly. And this is 0. Okay, now we have setup of squeeze theorem. So now if I write that, now limit of n approaches to infinity and 1 by n minus 1, which is equals to 0, and therefore this limit n approaches to 0, which is m equals to n plus 1 up to infinity, that is n factorial by m factorial equals to 0, right? Now we'll do the second property. So the second property, so if I just take these things here, so this setup, so I'll recall this setup, this squeeze theorem setup in second part. Okay, so while using the second property, okay, okay, so let me write that thing properly. So summation over m running up to n plus 1 to up to infinity, the n factorial by m factorial, which is lesser than 1 by n minus 1, and this. So you see this 0, so we need to change our lower bound, and you see that so from here, so we'll change this lower bound. Okay, again you see in this part, this entire part, so if you just carry forward this sum, so here 1 by n plus 1 and some more terms will be there, and that more terms after n plus 1, that's also positive. Okay, and notice that, see, if you carefully notice that this entire sum very first term of this sum 1 by n plus 1 plus more terms, and this more terms is positive. Okay, and we'll change this lower bound. Okay, so therefore the sum we are looking for is necessarily bigger than 1 by n plus 1. That is, so if we just write it again, so if you just write it down, so if you just change this 0, so instead of 0, what we take as our lower bound, we can take 1 by n plus 1, which is lesser than of this sum, which is m up to n plus 1 up to infinity. Okay, yeah, so in factorial m factorial lesser than 1 by n minus 1. Good. So which implies that n by, so I am multiplying it both side, so n, that is n plus 1 lesser than n times this summation n plus 1 by infinity in factorial by m factorial. Okay, and that is lesser than n by n minus 1. Good. So as n approaches towards infinity, that is, so limit n approaches to infinity for 1 by, so n by n plus 1, that is limit of n tends to infinity 1 by 1 plus n, so you know this will be 1. Again, if I take limit of n tends to infinity n by n minus 1, which is nothing but limit to 0 towards infinity, and this is 1 by 1 minus 1 by n, which is also 1. So if we implement the squeeze theorem, okay, so if we implement the squeeze theorem in it, so it will what, then the limit of n tending to infinity, that is n times m equals to n plus 1 to infinity, that is n factorial by m factorial, which is also 1. Okay, so this is our second property proved. So what is the third property? What does this third property will state? So suppose the third property, so next page we will prove this third property. So third property says that suppose epsilon, for a positive epsilon and this arbitrary positive epsilon for some delta positive, okay, such that if this x minus a will be evaluated in this, like this. So you know this definition, I guess. Then this function, this f of x, the mod of this. So if we find, so our objective is to find some n which is the set of belongs in the set of natural numbers, such that if n is greater than this n, so we have an minus a for some delta, okay. So notice that if n is greater than this some n, then modulus of n minus a is greater than this delta, which tell us which says that this f of n nice, so it has limit. So this is the inequality that we need to build to prove that limit of as x approaches to a and function of x which is L, and then can claim that limit n tends to infinity and this f of n, so here n is a sequence of real number, okay. So this is also L. Now we have got all these three properties which we want to build, and we are going to derive a value for this following limit. So what is the limit? The limit is this. So this is the following limit. So limit n tends to infinity n times sine, okay, 2 pi en factorial, okay. So this limit will help you to prove that E is irrational. So first thing we'll do is we'll expand E as infinite series, okay. So limit yeah, okay, fine. So limit, next step will be n towards infinity n times sine 2 pi and yeah. So I'm expanding E, and this n factorial I'll taking under this summation. That means this summation starting from m0 to infinity, and in factorial is already here. I am just taking it in numerator, and under denominator this is m factorial. Okay, so here we'll take the sum and break it into its integer part and the fractional part. Okay, so in this sum, okay, for this sum, okay, carefully observe that for this sum we'll take this sum and break it into its integer part and the fractional part, right? So yeah, and also notice that all of the parts where m is between 0 and n. Okay, so let me write it down first. So if I just yeah, let me use another color. So this summation 0 to up to this in factorial, which is equals to yeah, so this m running to 0 to up to infinity. Why I am writing this way, I am telling you. Okay, so I am justifying it. So in factorial plus m running up to n plus 1 up to infinity in factorial by m factorial. Okay, and this is my Zn and this is the an. Okay, so if you notice that all of the parts where m is between 0 and n, okay, that 0 and n are integers, because here we have the numerator is larger than the denominator and they are both factorial, so that both simplifies. So we can write this way. Okay, so I am again highlighting this. So in this way we can write this. Okay, yes. Yes. So we can write this limit as this limit n tends to infinity, that is n times sine of so as I will break it down, so I'll write is 2 pi Zn, okay, 2 pi Zn plus 2 pi An. Okay, so we will what can I do? Yeah, so we will read this term out. So this term, okay, so read this term out. Read this term. Okay, because of the periodicity of sine function. So sine 2 pi is periodic. That means we'll read the terms of 2 pi zn terms. Okay, so therefore we'll left with what? This terms, only this 2 pi n. Okay, so limit of n tends to infinity n times sine 2 pi 2 pi an, right? So we'll adjust it in some way that will apply this limit. Okay, so how we'll adjust? So here I am showing it. So if I just take the okay, so limit n approaches to infinity, okay, and so n times, okay, so 2 pi an here and 2 pi an here, and here it is sine 2 pi an. Okay, and I'll write this. So limit n times n approaches to infinity 2 pi n times an, okay, and this limit n approaches to infinity, so this sine 2 pi an, right, by 2 pi an. So now you know that this is the format of limit of sin x by x as n approaches to infinity. Okay, so this is nothing but what? So this is 1 and this is, so 2 pi, that will be in constant, so 2 pi times 1, so this is nothing but 2 pi. Okay, so the limit n tends to infinity n times sine 2 pi e n factorial, okay, so n factorial, okay, which is equals to two pi, right? Now we have just done the proving the complementary limit that will help to prove the E is irrational. How? Now we'll write that suppose E is rational. So this is the notation of rational number of set. So suppose E is rational. So we can write that in this way, that E is in P by Q format, where P is integer, okay, and this q belongs to set of natural number. Okay, and you notice that we can actually take them both natural number if this is a irrational number, because we know that e is positive, and furthermore if we wanted to so we could take this to have GCD of 1, which is pretty easy to see. So notice that if n, so yes, so notice that if n is greater than this q, so we have following setup. Which is problematic. Okay, which is problematic. So what is the setup? So if e times n factorial, so e is represented by p by q format. Okay, so p by q format, it is small p by q times n factorial, and we can break this n factorial. So p by q, so n times n minus 1. Okay, that is up to, so we can also adjust this q term, so q plus 1. Okay, q times q minus 1 dot dot up to 3 times 2 times 1, right? So this is a one kind of, you say, trick or method, or it's a clever way to deal with these things. So by solving problems, more and more problems, you will get to know how to deal with this sort of mathematical operations. Okay, so as n is greater than q, then, and q belonging to this set of natural numbers, so this sine of 2 pi e n factorial is sine of 2 pi bn. Okay, so 2 pi bn, I have written this en factorial as, so let me write, so this is also 0, where this bn is en factorial, and this bn belonging to this natural number. So you know that for the periodicity of sine function, so this is 0. Okay, so but we know that sine of any integer multiple of 2 pi is equal to 0, you know. So that means this sine function is equal to 0. Here you can see, and after some point, all of the time, but from the, it follows that, so if I take limit of so if I take limit n tends to infinity, that is n times sine of 2 pi en factorial, which is 0, so which contradict with our proved result, right? So that is 2 pi we have proved, and here it is 0. So according to this definition and how I justified, I am again saying that we know that sine of any integer, so you can, while you are proving this, you can also write this in this way, that we know that sine of any integer multiple of 2 pi is equal to 0, and then write this argument. So it will help you to understand, and others to justify, to make someone understand that why I am doing these things. Okay, so that means what? That means this sine function is equal to 0. So, and after some point, all of the time. Okay, so but from that it follows that this limit is 0, which contradict with our proved result. Therefore we can conclude that E is irrational. Therefore it is contradict with our proved result. Therefore E is irrational. So this is how we can prove the irrationality of how to prove that E is irrational. So there is another way to prove that E is irrational, that is quite, so if you can if you understand this process, do it yourself, and if you have any doubts and any question, so you can ask me in the chat box, the comment section. So you can how or do I need to justify more things, or so next video I'll upload that another way, so that is very compact way. So, and this is the whole things I have justified. So yeah, this is what I want to show you today. So thank you for your patience. So if you have any doubts, you can ask me question in a chat box, and yes, I'll paste my mail ID, so you can ask me in the mail, and you can follow me in my website. So thank you for listening. Thank you. So I'm ending up this session here.